everyone. Today we're going to be talking about, we're going to keep on with nuclear chemistry, and specifically we're talking about nuclear fission and fusion. All right, so these are two very high energy actions that we can make happen. All right, so we're going to look at fission first. So fission, if you think of the word fissure, you might think of like an earthquake that causes a break in the ground, right? A splitting or a fissure of the cement in the ground. So a fission reaction is one where we have a heavier nucleus that splits into lighter nuclei. So we have a heavy nucleus splits into lighter nuclei. Energy is released in this case, all right? That's the great thing about fission and fusion. These both have with them huge amounts of energy release. Fusion, on the other hand, now if you think of something fusing, it's more, instead of splitting, it's more of coming together, okay? So a fusion reaction is one in which you have two smaller, lighter nuclei. So smaller nuclei, and they're going to fuse to form a heavier nucleus, right? This is going to also release a lot of energy, and we're going to see how much energy in relation to each other. I have here a table of the differences between fission and fusion. So both of them require some kind of fuel source to make them happen, okay? So a fuel source for fission, two common ones, are uranium-235 and plutonium-239. All right, so these are very large nuclei if you look at them. 235 is the mass number, 239. So these are going to lend themselves to the heavier nucleus splitting and releasing energy, okay? In fission, these can happen in different places. So they can happen in a nuclear reactor where we can actually kind of control what's going on, or in atom bombs, not quite as controlled of reactions. The typical reaction, all right, so remember uranium-235 is a fuel source for it. So if we look at a typical reaction of uranium-235, what we see in fission reactions is that we always have a bombardment by 10N. What has a mass number of 1, no protons, and N? A neutron. Okay, so we see uranium-235 bombarded by a neutron. All right, so that neutron is a reactant. And it's going to cause the uranium-235, right, to split into smaller nuclei. We have krypton-92 and barium-141. We also have three neutrons that are also released. And because there's more neutrons released, we can actually have a chain reaction of these fission reactions because these neutrons can then go bombard other larger nuclei. The pros of fission. When we're talking about the pros of fission, we're thinking about nuclear energy, right? So in comparison to different kinds of energy that we have, burning of fossil fuels or coal, solar panels, stuff like that, we see that one pro of fission is that it actually produces 1,000 times more energy than burning coal. Remember that coal is not a renewable resource, all right? So we are running out of it. Fission produces 1,000 times the energy of that coal. That's awesome. It also does not produce any greenhouse gases, all right? So both very good things. The problem with nuclear fission, which we do use right now as a type of nuclear energy, is that there's radioactive waste produced, all right? That radioactive waste is very harmful if there's ever an accident, all right? So there's a possibility of nuclear accidents. We're actually going to look in class at some common nuclear accidents. I'm sure that you've heard of Chernobyl, you've heard of different recent accidents that have happened. There's also, and they really contaminate the air, they contaminate the water, they contaminate the land, and make it unlivable. It can make it unlivable for a long period of time if there are these nuclear accidents where the radioactive waste is spilled. It also opens the door of the possibility of using fission for terrorism, which obviously is not a good thing. Now let's take a look at fusion. This is the kind of ideal, if you will. Remember, we have two smaller nuclei coming together. They're fusing to form a heavier nucleus. The fuel source for fusion over there is hydrogen. All right, so hydrogen is the fuel source. Well, that's awesome because we have plenty of water, right? All throughout our Earth. I shouldn't really say that in California, but we have plenty of water, right? And that can be used as a hydrogen fuel source. That's awesome. It occurs in hydrogen bombs or naturally in sun and stars, right? Here's a common reaction that we might see, all right? So we have two hydrogen 3 nuclei combining with two hydrogen 1 nucleus to produce two helium 4 nuclei, all right? So remember, these top numbers are the mass number. We have a mass of 3, a mass of 1, combining to form a mass of 4, a larger nucleus, okay? Now, the pros of fusion. This produces 1,000,000 times the energy of burning coal. Not just 1,000 like fission, 1,000,000 times the energy of burning coal, right? So a lot more. There's also no greenhouse gas emissions, right, which is great. There's no radioactive waste with fusion. Even better, all right? So it has a one-up on fission right there. And we have a lot of water that we can use for the hydrogen fuel source. The cons, because there's always cons, is that it requires temperatures of millions of degrees Celsius, really high temperatures, in order to make these fusion reactions happen. And as of yet, we haven't actually been able to make those temperatures happen or sustain them on Earth, all right? So we haven't actually been able to make that happen. So we're going to look at a couple of different types of reactions and determine whether or not they are fission or fusion. Before we do that, I want to just go over a couple little quick checks to make sure that we're all on the same page. And we know what I mean when we're saying heavier nucleus, lighter nucleus. All right, so in each pair up here, so we're going to look at the A, black, and then the B, the red. Which nucleus is heavier? Okay, so we have uranium-235, plutonium-239. Which one's heavier, right? Hopefully you see that plutonium-239 is heavier because it has a larger mass number, or A. Remember A and Z? A is our mass number, right? So plutonium has a larger mass number. How about if we're looking at helium, 4-2 helium, 3-2 helium? Which one is larger? Which one's heavier? Hopefully you again see that 4 is larger than 3. So 4-2 helium is the heavier nucleus compared to 3-2 helium. You need to know that basically in order to be able to figure out whether a fusion or fission reaction is happening. All right, so here's kind of a short example. In a fusion reaction, two nuclei of H2, that's hydrogen 2, combine to form a nucleus of what? And here's our options. Hydrogen 4, helium 4, helium 2, lithium 4. All right, so like any good student, I know that you're thinking, well, I need to write out this reaction and see what's going to happen because I can't just look at the answers and choose one. You're right. All right, so we have hydrogen 2 and hydrogen 2. Oh. Right? We need to fill in the atomic numbers, the Z, right? We have the A. What's the Z? Well, if you look at the periodic table for hydrogen, hopefully you know hydrogen is the very first element. So it has atomic number 1, has 1 proton. So we have 2 nuclei of hydrogen. What are they going to combine to form? 2 plus 2 gives me 4. 1 plus 1 gives me 2. All right? And what's produced? Helium, because helium is atomic number 2. Now, you might be saying to yourself, well, wait a minute, this looks like an alpha decay problem, right? This must be alpha decay because an alpha particle is produced. Remember that in alpha decay, we have one reactant that is producing the alpha particle and another nucleus. Here, this is the only product, all right? So this is not alpha decay. This is a fusion reaction, right? So what's produced? Helium 4. and B is our correct answer. All right, now we're going to take a look at a couple more problems just like that. And I'm going to throw in a little tricky one at the end for you. All right, so we need to figure out whether each of these is a fission or fusion reaction and why. All right, so here we're looking at, we have uranium-235 and a neutron. Your brain should immediately be thinking, uranium is its fuel source. It's bombarded by a neutron. This is probably going to be fission. Let's check, all right? We have strontium-90, and we have 3 neutrons also produced, all right? So, 235 and 1, 236, minus 90, minus 3, because 3 times 1 is 3, and we get 143 as our mass number. 92 plus 0, 92, minus 38, minus 0, and we get 54. Now, if you look on the periodic table, element 54 is xenon, all right? And we have a larger nucleus bombarded by a neutron splitting into 2 lighter nuclei. What is this? We're confirming it is a fission reaction, right? I'm not going to write down the justification, but it might be good of you to do it right now because I don't have time, but you do if you pause this. All right, the second one, we have hydrogen 2 and hydrogen 3 combining to produce an unknown product and 1 neutron. Let's fill in the Z numbers, the atomic number, because we need to know these. Hydrogen has an atomic number of 1. A neutron has no protons. All right, so now we can figure out our missing nucleus. We have 2 plus 3 for our mass number over here, and we have 1 neutron over here. So 5 minus 1 gives me 4, okay? Now I have 1 plus 1, that gives me 2, minus 0, 2. We'll look at this again. 4, 2, what's atomic number 2? Helium, all right? Again, you might be thinking, this looks like an alpha decay reaction. But no, remember, alpha decay has 1 reactant that's producing an alpha particle and another nucleus. Not just a neutron, a nucleus. Okay, so this is not alpha decay. We have 2 smaller nuclei coming together to form a bigger nucleus. This is a fusion reaction. You need to be able to justify that like I just did. All right, the third one, we have uranium-235 plus a neutron. Well, I know uranium has an atomic number of 92. I know that a neutron has no protons. I know that krypton, oh, this is a good one to look up, krypton has an atomic number of 36. And I have 3 neutrons over here. If I do the math, 236 minus 92 minus 3, I see that I have a mass number of 141 left. 92 minus 36 gives me an atomic number of 56, which on the periodic table is barium. Okay? Uranium as a fuel source, very large nucleus, bombarded by a neutron, splitting into 2 smaller nuclei. This is fission. Now my last one. Here's where I'm throwing in the trick. I have 241, I can never say this right, 241 decaying into NP-237. All right, now if you want to look on the periodic table, you can find NP, which is neptunium. All right, 237, what else is left? All right, 241 minus 237 gives me 4. 95 minus 93 gives me 2. Well, wait a minute, atomic number 2, we already know that that is helium, right? Now you might be thinking, wait, Miss Frankovic, this looks like an alpha decay problem, all right? Because you have 1 nucleus, right, producing an alpha particle and another nucleus. You're right. This is alpha decay, right? Your practice is going to involve not just fission and fusion reactions. You're going to have beta decay, alpha decay, electron capture, and you're going to need to figure out which is which, all right? So you're going to have all of those choices to choose from. You need to be able to use that reasoning to figure out the correct decay or reaction.